Hello everyone. In this video, we are going to see the analysis of BJT with the fixed bias and the voltage divider bias. So we are going to analyze a BJT circuit with these two types of biasing. For that, first we have to see the concept of this. So in simple, the aim of the experiment is to analyze the BJT with the fixed bias and the voltage divider bias, especially using the software known as the multisim. So what is biasing? So it is a process of setting a DC operating point, that is a voltage and current condition, to the correct level. Why we have to do that in a sense? So that only any AC input signal can be amplified correctly by the transistor. So this steady state operation of the transistor depends upon the base current, collector voltage and the collector current, that is IB, VCE and VC. This is IC. Okay, so these values are very important, and the transistor is to operate correctly as a linear amplifier. So this point is known as the operating point. This operating point is also known as Q point. So this Q point is nothing but this VCE and IC. So in simple way, we are biasing the circuit so that we can amplify in the current manner. For that, we have to find this 2 point, which is VCE and IC. So next, there are so many biasing method for biasing this BJT. First, we have to see the simplest method, which is a fixed bias. So the name itself shows it is a fixed base bias circuit. In this, the IB remains constant. Therefore, the operating point is also remain constant. So here there are two resistors which construct the network so that the initial operation region is established. So this is that two resistor, which is RB and RC. And also this type of resistor is known as a beta dependent circuit, because here the steady state condition is a function of beta. Here we apply the forward biasing in the positive base bias voltage via this current limiting resistor RB. So we are applying a forward bias here. So in we can see this is a input circuit, which is a base circuit. So in this input circuit, if we analyze this, we can get the IB value. So by applying the KVL, we can get this IB value from this input base circuit. So this is the output collector circuit. So this is the output circuit. In this, we can get VCE value. So from this IB value, later we can get this IC value from the relation of beta IB. So from the input and output circuit, we get this VCE and IC Q points. Now we are going to construct the fixed bias circuit. For that, first we have to click this place and then component in that basic, and then we have to select this resistor. Here we want 220K resistor for our circuit. So then click OK. We can get this. And then if we want another resistor in the sense, we have to again click that. And now we want 1.2K resistor. After choosing, we have to click OK. So place this. Then now we want an transistor. For that, we have to choose this transistor. And in that, we want BC BC107 PB. So this transistor we want, you have to click on this. Then we want one power supply VCC. For that, we have to go for the source and then power supply. So we want VCC. So this VCC of 5 volt, but we want 10 volt. For that, we have to double click on that. Then value, then we can change the value here 10. Then click OK. So then we want a ground. So ground, then click OK. So these are the required components we want. So now we have to connect it. For that, we can use the wires. So wires, we can click from the place wires. We can rotate this by right clicking it. This we have to connect. Then we have, we want a BJT analyzer to analyze our DC load line. So here the CEB is mentioned and we have to connect according to that. First, we have to connect this in. So this is our fixed bias circuit. Here we construct the fixed bias circuit. So this R1 shows the RB, this R2 shows the RC, and this is our transistor with a beta value 50. And here we give the power supply of 10 volt. So first we have to check the VCE value and the IC value. So which is our Q point, right? So first we have to check this two value. For that, first we have to set this DC operating point. So there are so many mode. If it is in some other mode, first we have to switch it to the DC operating point. And here, first we have to set this variable. So for the IC value, we have to choose the IC. Then for the VCE, so we already seen that VCE is VC minus. So VCE is VC minus VE. Where this VC value is 0. So the VC is VE is 0. So the VC alone is enough. So here the VC is 1. Okay. So for the clear picture, we have to erase this one. Okay. So now we see this. Okay. V1 1 is nothing but the VC value. So after setting this all, we have to select the expression from here and add, and after selecting here, we have to run this. Okay, so here we can observe our VC value is, so this is our VC value and this is our IC value. So this here we can cross verify our fixed bias value of IC and VCE. So we take VCC as 10, beta as 50, and RB as 220 kilo ohm, and RC as 1.2 kilo ohm. And after substituting these value in this formula, the IB value is 42.27 microampere. So usually IB is in the microampere. The IC is beta into IB. So here the IC is 2.113 milliampere. So usually IC is in the milliamps. And then after substituting in the KVL, the VCE is 7.46 volt. So this the IC value and IB value are similar to the value what we get in the multi-sim. So there is some mismatch in this point value, but the overall value is very closer to our multi-sim value. So thus we can cross verify our multi-sim value with this manual method. Now we are going to see the DC load line graph of this fixed bias. For that only we are connecting this BJT analyzer. So here it is given like a BE. According to that, we have to connect this in the circuit. And for that, we have to set this mode into interactive mode. And after that, we can run this. And we can click this BJT analyzer. Here we can saw the graph of DC load line. So in this x-axis is a VCE, y-axis is IC. This different color line shows the IB value at the different levels. So here we can change this value according to our calculation value also. So now I change this VCE value and IB value according to our calculation. And now you can observe this graph. So this is the DC load line graph. And that's all about the fixed bias. Now we're going to see about the voltage divider bias. So among all the biasing method, this voltage divider bias is most prominent one, and it is give the better stabilization. Here the two resistors R1 and R2 are given, and which is connected to the power supply VCC, and this RE is employed in the emitter, which provides this stabilization. So the name itself gives that voltage divider. So this R1 and R2 providing the voltage divider or the potential divider network. So here the voltage drop across R2 is forward biases the base emitter junction, and this causes the base current IB. Hence the collector current flows in the zero signal condition. And this is our input circuit, which is a base circuit. And if we apply the KVL in this base circuit, we will get this IB equation. Okay, we will get this IB equation. And so this is our collector circuit. So if we apply the KVL here, we will get the VCE. So from the IB, we can get the IC. So there's an introduction or the concept of this voltage divider bias. So we want to know why this voltage divider bias is somewhat special than the other biasing circuit, because it is independent of the beta. So we saw that the fixed bias is dependent on the beta, but it is independent of the beta. So it is independent of the transistor parameter. So the IC does not affected by the VBE. So it gives the better stabilization. If there is a rise in temperature also, the collector current IC decreases, but eventually the voltage in the RE is increased. So so that the VBE decreases, which reduces the IB. So the IC is restored to its original value. So whatever happens, even in the case of the temperature rise, the IB is retains their original value. So this is very important for the biasing circuit. So it is more stable than the other biasing circuit. Now we are going to implement this in the multisim. So this is our voltage divider circuit, which we saw before. So the same circuit I construct in the multisim software. So it is R1, R2, RE, RC, and this is a transistor with the beta value of 50, and it is a BJT analyzer. So here, if we want to find the Q point, we have to set the DC mode as the previous. And here we run this. So we get our VCE and the IB value. So this is a VCE value and it is a IB value. So VCE value is 4.50431 and the IC value is 1.9772 milliampere. Okay, so IC is usually in the milliamps. So we get this, and we have to cross verify it by our manual method. So this is our manual calculation for the voltage divider bias, where we use the formula of the IB is 39.4 microamps, usually IB in micro and IC in the milliamps. So the IC is nothing but the beta into IB. We get the 1.97 milliamps, exactly what we get in the multisim, and the VCE. So for that, we have to apply the KVL in the output circuit, and substituting the values in the formula, we get 4.757. This is also exactly what the value we get in the multisim. So our manual method and multisim method is matching. Now we are going to see the DC load line graph of this voltage divided bias. For that, we have to change our mode from the DC operating point to the interaction simulation, and we have to run this. And we have to double click this BJT analyzer. Here we can clearly see the graph or DC operating point graph. Here in the x-axis it is VCE and it is y-axis it is IC. Here it is VCE and IB. We can change our value according to our circuit value. We can change this. So this is Hemamali presenting this video, and my batchmates are Akram S, Kannan G, Shaktipriya S. Thank you for watching.